right, let's finish up 9.1. So this is 9.1 part 2. All right, so this should look familiar. We did hypothesis testing in chapter 7. For this one, we're only going to use a two-tailed test, and we're going to do it on what is called rho. So this is a Greek letter. It kind of looks like a P, but it's actually called rho. Right. So what we're going to be testing is the null hypothesis is going to be that there is no significant correlation. In other words, the population correlation coefficient rho would equal 0. And then our alternative is that it's not equal to 0. We're going to be using a t-test for this. We're still going to use StatCrunch, of course, so we don't have to worry about a lot of this. But we do have to, a little bit different of a degrees of freedom. So because we have two variables, this time our degrees of freedom is going to be n minus 2. Remember before when we did a t-test in chapter 6, we had n minus 1, but we only had one variable. Now we have two variables, and so our degrees of freedom is going to be n minus 2. Otherwise, we're going to do this just like our hypothesis testing in chapter 7. We're going to have a null hypothesis, an alternative hypothesis. We're going to be given a level of significance. We're going to be given all of the data we need to put this into the test. And then finally, we're going to get to the end and we're going to reject or we're going to fail to reject. All right, so let's take a look here. We have, we're going to use 10 pairs of data. So n is equal to 10. We found that R was 0.874. We're going to test, we're going to do a hypothesis test. And so we're going to have the null hypothesis is that rho is equal to 0. The alternative is that rho is not equal to 0. It's going to be a two-tailed test. I'm going to show you on a later slide how we can actually get this value. I have it here where you're using a calculator and you're using the information you know. So you're using that n is equal to 10 and that R is equal to 0.874. But this is kind of a beast to get in your calculator. So a little later, I'm going to show you how to do that in StatCrunch. But let's say for this one that we put this in our calculator. Now, the problem is we need to look at our critical values for alpha. And also remember, because this is a two-tailed test, I have to split alpha up into each side. So alpha is 5%. That means I have to split each of these up and put 2.5% in each end. And so that's why when I went to do the T calculator to get my critical values, the area here is the 0.025. Okay, so I had to put my degrees of freedom here. Remember, degrees of freedom for this is n minus 2, so it would be 10 minus 2 or 8. And then I put in my 2.5% on that side, and I get a critical value of negative 2.306. Now remember, because this is a two-tailed, if it's negative 2.306 on this side, then it's going to be positive 2.306 on this side, right? This is all just like we were doing in chapter 7. Nothing has changed. All right, so let's take a look here. Here's the graph again. I had to take my alpha of 5%, my significance level, and split it into both tails. So in one tail is 2.5%, in the other tail is the other 2.5%. I found my critical values, so I had negative 2.306 and positive 2.306. And so those are my rejection regions, right? The blue shaded area are the rejection regions, just like they were in chapter 7. Now, my data value, the value that came from my data that we found on the other page was 5.087. Well, that's way over here. So that is definitely in the rejection region. But what we have to be careful of is that we're rejecting that there's no correlation. Okay, we're rejecting that the population R or rho is equal to 0. So if we reject that, then we have enough evidence at a 5% significance level to conclude that there is actually a strong linear correlation between the two. And we were pretty sure of that because we saw that R was about 87%. And so we knew we had a pretty strong correlation, but this just more shows us. Now we do have to be a little careful about correlation and causation because there's websites on the internet that will take two things that totally don't have anything to do with each other, and they'll show that they have a really high correlation coefficient. So we can force data to look like it's correlated when it's really not. And so you really have to be careful when you're looking at these studies and saying that there's a significant correlation. All right, so here we have that it definitely made sense with the gross domestic product and the carbon dioxide emissions. I mean, if people are out buying lots of cars and trucks because they have money and they're spending money, then we're definitely going to have more carbon dioxide emissions. And so that was reasonable to make, and sure enough, our data showed that we had a strong correlation there. But sometimes it could be the opposite. Sometimes the variables have a positive linear correlation, but it doesn't mean that there's actually that cause and effect relationship between the variables. And so we do have to be very careful when we create studies. We also have to be careful because a lot of times something else is controlling the relationship, not just the x and the y. So there could be a third variable or maybe other variables that are actually making that be a positive linear correlation. So, or it could be a coincidence. So I'm going to let you read through this as you have a moment. I'm going to keep moving. All right, so this is an example of one of our problems. They gave us this huge data set where, what are we looking at here? The maximum weights in kilograms for which one repetition of a half squat can be performed and the time in seconds to run a 10-meter sprint. Okay, so they took 12 soccer players and they looked at the maximum weight they could do for one repetition of a half squat. And then they also looked at their times in seconds to run a 10-meter sprint, and they were going to compare these two. Well, when they compared them, they got a sample correlation coefficient of R equals negative 0.937. So pretty strong negative correlation, meaning the more weight they can do, the faster they're going to run. They added a 13th point and they want us to do the work. So what we're going to do is we're going to click on this box right next to the data. The 13th point is already in there, I think. We might have to add it. Let me see what this says. Nope, it was added on the bottom. Okay, so we're going to click on that box. We're going to go into, we're going to come not to summary stats. We're going to do stat. We're going to come down here to regression and simple linear. And then we're going to put the weight in the x variable, the time in the y variable. We're going to hit compute, and it's going to give us our new correlation coefficient. Ooh, this guy messed up our correlation coefficient a little bit. So now it's gone down to negative 0.687. It was up at negative 0.937. So it's actually getting weaker, right? It's not as strong. We had a very strong negative correlation before when we added just that one data point on the end. It came down. It's still it's an okay negative correlation, but it is definitely weaker than what we had before. And that's because it's closer to 0 and not as close to 1, well, negative 1. Okay, so again, they're giving me data. They gave me the number of hours 10 students spent studying for a test and their test scores. So again, when we're ready, we're going to hit this box here. But first, let's see what they want. First, they want the hypothesis. So remember that first we're going to have our null hypothesis is that there's no correlation, that rho is equal to 0. And our alternative is that it's not equal to. So this is a two-tailed test. Alpha was 0.1. So remember, we have to split that 1% into both tails because this is a two-tailed test, because it's not equal to. And so I came over here and used my T calculator. My degrees of freedom was n minus 2, which was 8. I was doing my left tail first, and I put 0.5% in for the area. That gave me my critical value on the left side of negative 3.355. And then because of symmetry, I know that the positive side is 3.355. All right, so this one wanted me to look at the test statistic. So that's fine. What I did was I clicked on my data box here, and I went to regression again. I went to regression and simple linear. I put the hours in for X. I put the test score in for Y. And notice if you come down a little bit after you hit compute, there's actually a test statistic here for the intercept and for the slope. We're going to use the slope. And so we're going to use this 9.183. That is the test statistic for the slope. And we're going to compare it to our data. But it's huge. Look at that. 9.185 is way over on the number line, like way over here somewhere. Definitely in the rejection region. So we are going to reject our null hypothesis that there is no significance and there's no correlation, and we're going to support the claim that there is correlation. And the whole reason we're doing that is look at that correlation coefficient. It is positive 0.956. That's almost 1. And so we can be pretty sure that that is a nice, strong correlation. But it's still good to do the hypothesis test and see. So again, since our test statistic was so much bigger than our critical value, it was way over in the rejection region. So we're going to reject the null hypothesis, which means there's no correlation, right? We're rejecting that there's no correlation, and we're going to support the claim that there is a correlation.